In this video, we're going to start practicing using material balances. In fact, we're going to first focus on what I call molecular material balances, in which each species in the material balance is a separate molecule or chemical entity. Okay? So, let's first focus on using molecular material balances where each species is a separate molecule. Or chemical entity. Okay? And the example we're going to start with is going to deal with the distillation of a benzene and toluene mixture. Okay. So in your MEB 1 class, you probably did quite a few problems that dealt with distillation. But I want to go over exactly, why distillation keeps showing up in these mass and energy balance problems. And so what I have here are a couple of slides that go through, what exactly the distillation process is. Okay? And so you may have, heard the term distillation starting in your organic chemistry course. And what you see here on this slide is a schematic of what a lab-scale distillation setup looks like. Right? And so what we have here is a round bottom flask on the left-hand side that's filled with a liquid mixture. Okay? And so let's imagine that this liquid mixture, it's not just containing one chemical species, it's actually containing multiple. Right? And so in this case, let's just pretend that it only has two chemical species in it. Okay, so two chemicals in this liquid. All right, and for the two chemicals, we're going to say one is volatile, while the other species is less volatile. Okay? And so by the word volatile, I mean it's more likely to vaporize when you heat it. Okay? And so we have this liquid mixture in this round bottom flask, and it's being heated by a heating plate. Okay? And so by doing this, this causes some of the liquid to evaporate. And so in here, above the liquid, we have a headspace that's filled with a vapor. Now, this vapor is not going to have the same concentration or the same mole fractions as the liquid. And that's because when things evaporate, the chemical that is more volatile will be more likely to evaporate than the chemical that is less volatile. And so this vapor becomes enriched, as we say, in volatile chemical. Right? Okay, and so this vapor is enriched in the volatile chemical, and it comes up from the liquid, vaporizes, and it goes through, and as it starts passing through this distillation setup, it goes to a section of the setup that's cooled by water. Right? And so here, it starts cooling the vapor, and this causes the vapor to condense back into a liquid. Right? But because that vapor was enriched in the volatile component, you end up having a product that's also enriched in the volatile component. Right? And so by doing distillation, you could purify your chemicals, right, after you do a reaction. Right? And so this is, the basic concept of how a lab scale distillation occurs. But the same concept is, or industrial scale distillations use basically the same concept. Okay? And so what I have here is a schematic for a distillation column that's used on the industrial scale. And so basically what you have is some feed stream that goes into your distillation column, right? You'll learn more about the distillation column for the chemical engineers. You'll learn more about it in your separations class. But it's basically filled with a bunch of different stages that heat the liquid and the vapor that form. All right? But in the end, what you get is a top product that's enriched in the volatile component and a bottom product that's mostly the less volatile component. Right? So it's the same concept that we saw on the Labscale distillation column. And so these are just schematics, but I also have pictures of what these things actually look like. Right? So here's the Labscale setup. And then at the bottom here is what industrial distillation columns look like. Right? And so this is, orders of magnitude bigger than what you see here. But they work both the same way. All right, and so distillation is an important tool for purifying chemicals both at the lab scale and at the industrial scale. All right, and so that's why we see it so much in these mass and energy balance problems. All right, so going back to our notes, we're going to do an example problem based around the distillation of benzene and toluene. Right, and we're going to use this, we're going to go through this example so that we get practice using material balances. Okay? All right, and so for this problem, I'm going to, first thing I want to say is that our basis for the problem is we're going to have a feed stream going in that has a flow rate of 1,000 kilograms per hour for feed. All right, so I'm just going to put that first. All right, and now I'm going to draw the process flow diagram for this distillation. All right, and so here's a diagram of my distillation column. It's just going to be a rectangle, distill. All right, and I said we have a basis of 1,000 kilograms per hour of feed going in to the column. So I'm going to draw my feed stream. I'm going to call this feed stream stream 1, right? And anytime I draw a stream, I'm going to put the ID for this stream right above the arrow and then circle that ID. All right, so here, stream 1 is going to correspond to our feed stream. Okay, and so in our feed stream 1, we have two different species. Okay, we have our benzene and we have our toluene. So the M dots here are going to be mass flow rates. All right, and so I put the 1 here so that identifies what stream this flow rate belongs to. And then the comma letter tells you what species that flow rate belongs to, right? And so the M1B here is the benzene flow rate in the feed, and we're going to say that it has a value of 500 kilograms per hour. Well, for the toluene, its flow rate is also going to be 500 kilograms per hour. And so this is the feed stream going into the distillation column. And we're also going to have two streams coming out of the distillation column. We're going to have our top product stream, which is going to be enriched in the more volatile component. So I'm going to call that stream 2. And then we're going to have a bottom stream, stream 3, that's enriched in the less volatile component. All right? And so in stream 2, the top product stream, it's going to be enriched in the more volatile component, which is the benzene. And benzene is more volatile than toluene because it has a lower boiling point at atmospheric pressure. All right? And so our M2B stream is going to have a flow rate of 450 kilograms per hour. our bottom stream is going to be the opposite. It's going to be more enriched in the toluene, right? And our toluene flow rate should be at 3. Our toluene flow rate is going to be 475 kilograms per hour. Okay? All right, and so these are the values that are given. What's not given initially is the flow rate of the toluene in the top stream. And we are also not given the flow rate of benzene in the bottom stream. And so for this example problem, what we want to do is we want to find out what M2T and M2B are. And we're going to do this by using material balances.